Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in. Let your body relax wherever you are. Adjust your pillow, there's no rush. We have all the time we need. Where in the world are you watching from? A quiet room as the day finally ends. Perhaps a peaceful corner where you can let everything go. Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most profound measurements humans have ever made. The actual size of the universe. Not just how far we can see, but how large the universe truly is, including the parts we can never observe. Scientists have finally determined this number, and it's more extraordinary than most people realize. But don't worry. This isn't going to be an overwhelming flood of incomprehensible numbers. Instead, we'll move slowly and carefully through one of science's greatest achievements, learning how we measured something so vast, what the different size measurements mean, and why understanding the universe's size matters for everything from the Big Bang to our cosmic future. If you enjoy these calm explorations of cosmic scale and discovery, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in, let your shoulders drop, take a slow, deep breath, and let it out even more slowly. And let's begin our slow drift through the measurements that have revealed the universe's true size. There's nowhere you need to be. Just listen, and let the story unfold. Let your thoughts expand into the vastness we're about to explore. Let's start with what we can actually see, because this is where the story of measuring the universe begins. The observable universe is the region of space from which light has had time to reach us since the Big Bang. This might sound simple, but it's surprisingly complex. The universe is about 13.8 billion years old. You might think that means we can see 13.8 billion light years in every direction, making the observable universe about 27.6 billion light years across. But that's not quite right. The universe has been expanding during all that time. While light from distant galaxies travelled toward us, space itself was stretching, carrying those galaxies farther away. This expansion affects how far we can see and how large the observable universe actually is. The current measurement, based on precise observations and careful calculations, puts the radius of the observable universe at about 46.5 billion light years. That makes the diameter about 93 billion light years. This is the distance to the cosmic horizon in every direction, the farthest we could possibly see. Let that settle for a moment. 93 billion light years across. Light travelling at 300,000 kilometers per second, the fastest speed possible, would take 93 billion years to cross the observable universe at its current size. No human timescale can capture this vastness, but this is just what we can observe. The observable universe is like a sphere around us, with Earth at the centre, not because we're special, but simply because we're the observers. Every point in space has its own observable universe, a sphere of the same size centred on that location. The edge of the observable universe isn't a physical boundary. It's a horizon, similar to how the horizon on Earth isn't a wall, but simply the limit of how far we can see. Beyond the cosmic horizon are regions of space that are so far away that light from them hasn't had time to reach us yet. As time passes, this horizon expands. Light from more distant regions reaches us, revealing galaxies we couldn't see before. In principle, we should be able to see more of the universe as it ages. However, there's a complication we'll discuss later. The universe's expansion is accelerating, which changes this picture. How do we know the observable universe is 93 billion light years across? The measurement comes from combining several observations. We know the universe's age from the cosmic microwave background, and from the properties of the oldest stars. We know the expansion rate from observations of distant galaxies and supernovae. Cosmologists use these measurements in the equations of general relativity, Einstein's theory of gravity that describes how the universe expands. The equations predict how far light could have travelled since the Big Bang, accounting for the expansion of space during that journey. The cosmic microwave background is particularly important. This is the oldest light we can observe, released when the universe was just 380,000 years old. By measuring its properties precisely, satellites like WMAP and Planck have determined the universe's composition, age, and expansion history with remarkable accuracy. Those measurements tell us that the observable universe contains about 2 trillion galaxies. That's a rough estimate. The actual number could be somewhat higher or lower. Each galaxy contains hundreds of billions of stars on average. The total number of stars in the observable universe is staggering, perhaps 10 to the 24th power, a 1 followed by 24 zeros. So when we talk about the observable universe's size, we're describing a region 93 billion light-years across, containing 2 trillion galaxies, countless stars, vast amounts of dark matter, and permeated by dark energy. This is the cosmic arena we can study, the stage on which all observable cosmic history has played out. But here's the profound question. Is this all there is? Or does the universe extend beyond what we can observe? And if it does, how much larger might it be? These questions lead us to think about the universe's total size, not just the observable portion. Most cosmologists believe the universe is much larger than the observable part, possibly infinite. The observable universe would then be just a tiny bubble within a vastly larger whole. But how can we know anything about regions we can't observe? How can we measure something we can never see? These are the questions we'll explore together. The answer involves some of the most sophisticated thinking in modern cosmology, combining observations, theory, and careful reasoning about what we can and cannot know. It's a journey to the edge of knowledge itself. Before we go further, we need to understand that the universe has several different sizes, each measuring something different. This might seem confusing at first, but understanding these distinctions will clarify what scientists mean when they talk about the universe's size. The first is the observable universe we just discussed, the region from which light has had time to reach us. This is about 93 billion light-years in diameter. It's a sphere centered on Earth, defined by how far light could have travelled since the Big Bang, accounting for cosmic expansion. The second is the particle horizon, which is essentially the same as the observable universe's edge. It's the boundary beyond which events could not have affected us, because not enough time has passed for light or any signal to reach us from beyond that distance. The fifth, and most interesting for our discussion, is the universe's total size. This is how large the entire universe is, including parts beyond our observable horizon. This could be finite but much larger than the observable universe, or it could be infinite. Determining which is one of cosmology's great challenges. Each of these sizes tells us something different. The observable universe's size tells us how much of the cosmos we can study. The Hubble radius tells us about the expansion rate. The event horizon tells us about the universe's future, and the total size tells us about the universe's overall geometry and structure. Let's focus on what makes these different. Imagine you're standing in a vast fog-covered plain. The observable universe is like the circle around you within which the fog is thin enough to see. The Hubble sphere is like the distance where objects become so obscured by the fog they blur into invisibility. The event horizon is the distance beyond which the fog is thickening so fast that you'll never see what's there, even if you wait forever. And the total size, that's the actual size of the plane itself, which might extend far beyond your visible horizon or might even go on forever. You can't see it directly, but you can make inferences about it from what you observe within your limited view. The observable universe's size has grown over time and will continue growing, but at a decreasing rate due to accelerating expansion. Eventually the event horizon will stop expanding and no new galaxies will become visible. In the far future, only nearby galaxies will remain visible. Everything else will have receded beyond the event horizon. Understanding these distinctions is crucial because when scientists talk about measuring the universe's size, they mean different things in different contexts. Measuring the observable universe is straightforward. We observe the cosmic microwave background and calculate how far that light has travelled. That gives us the 93 billion light-year figure. Which is it? Measurements of the cosmic microwave background have determined that the universe is extremely close to flat. Perhaps exactly flat. This suggests it's either infinite or, if finite, much larger than the observable universe. We'll explore this in more detail later, but for now, understand that flatness is a crucial clue about total size. These different size measures can seem abstract, but they're all rigorously defined and observationally constrained. Scientists aren't guessing, they're using general relativity and precise measurements to determine these cosmic dimensions. Each size tells part of the story of how large the universe is and how it has evolved. To understand the universe's total size, we must understand its geometry, its overall shape. This is one of the most profound questions in cosmology, and the answer has been painstakingly determined through decades of observations. General relativity, Einstein's theory of gravity, describes how matter and energy curve space and time. On cosmic scales, this curvature determines the universe's overall geometry. Depending on the total density of matter and energy, the universe can be flat, spherical, or hyperbolic. Imagine drawing a triangle on different surfaces. On a flat plane, the angles sum to exactly 180 degrees. On a sphere's surface, like Earth, the angles sum to more than 180 degrees. On a saddle-shaped surface, they sum to less. These are examples of positive curvature, zero curvature, and negative curvature. The universe's three-dimensional space has similar properties, though they're harder to visualize. In a positively curved universe, parallel lines eventually converge. In a flat universe, they remain parallel forever. In a negatively curved universe, they diverge. Multiple satellites have measured the cosmic microwave background with increasing precision. COBE in the early 1990s made the first detection of fluctuations. WMAP, operating from 2001 to 2010, measured them in detail. Planck, operating from 2009 to 2013, achieved the highest precision yet. Planck's results are stunning. The universe's geometry is flat within a fraction of a percent. The curvature parameter, which would be 0 for exact flatness, is measured to be 0.0004 plus or minus 0.0005. Statistically, this is consistent with perfect flatness. This flatness is extraordinary. It means the universe's density is almost exactly the critical density. Matter, and dark energy add up to just the right amount to produce a flat universe. This seems like an unlikely coincidence unless something in the early universe drove it to flatness. Cosmic inflation, a period of exponential expansion in the universe's first fraction of a second, provides an explanation. Inflation stretches any initial curvature to negligible levels, making the universe extremely flat. The fact that we observe flatness supports inflation theory. But flatness alone doesn't tell us if the universe is finite or infinite. A flat universe could be infinite, extending forever with uniform properties. Or it could be finite with a topology like a three-dimensional torus, where you'd return to your starting point after travelling far enough in any direction. Think of a video game where moving off one edge of the screen makes you appear on the opposite edge. The screen is flat locally, but it has a finite connected topology globally. A flat universe could work similarly in 3 dimensions. Distinguishing between infinite and finite flat topologies requires different observations. If the universe has a finite topology smaller than the observable universe, we might see repeating patterns in the cosmic microwave background, where photons have travelled all the way around the universe, and we're seeing the same structures from different angles. Searches for such patterns have found nothing definitive. This suggests that if the universe is finite, its total size is much larger than the observable universe, at least several times larger. Otherwise, we'd likely have detected the repetition. Current estimates suggest that if the universe is finite, it must be at least 250 times larger than the observable universe in diameter. That would make it at least 23,000 billion light-years across, vastly larger than the 93 billion light-year observable region. But many cosmologists suspect the universe is actually infinite. Perfect flatness, as we seem to observe, naturally leads to infinity. The universe would extend forever in all directions, with galaxies and structures continuing without end beyond our cosmic horizon. This raises profound philosophical questions. An infinite universe would contain an infinite number of galaxies, stars, and planets. In principle, it would contain every possible configuration of matter, including infinite copies of you reading these words. These aren't just thought experiments, but logical consequences of infinity. However, we can never prove the universe is infinite through observation. We can only observe a finite region. We can rule out certain finite sizes if they're smaller than the observable universe, but we can't distinguish between a very large finite universe and an infinite one. The geometry question demonstrates how cosmology works at its frontiers. We combine observations, particularly of the cosmic microwave background, with theory, particularly general relativity, to constrain the universe's properties. We can't see the whole universe, but we can infer much about it from what we can see. The conclusion is remarkable. The universe is flat, or very nearly so, implying it's either infinite or vastly larger than the observable region. This flatness is one of the great discoveries of modern cosmology, revealed through patient measurement of ancient light from the cosmic dawn. If the universe is infinite, as many cosmologists believe, what does that really mean? Infinity is a concept that's easy to state but difficult to truly grasp. Let's think carefully about what an infinite universe would imply. First, an infinite universe contains an infinite amount of space. There's no edge, no boundary, no centre. Every point is equivalent to every other. No matter where you are, you could travel forever in any direction and never reach an end. This isn't just very large, it's limitless. The difference between very large and infinite is absolute. A finite universe, no matter how vast, is still bounded. An infinite universe has no bounds at all. It's a qualitative difference, not just quantitative. An infinite universe would contain an infinite number of galaxies. If galaxies are distributed relatively uniformly, as observations suggest they are on large scales, then infinity of space means infinity of galaxies. Each galaxy contains billions of stars, so there would be infinitely many stars, infinitely many planets. Here's where it gets stranger. In an infinite universe with finite possibilities for how matter can arrange itself, every possible configuration must occur infinitely many times. This includes complex, unlikely configurations. There's a finite number of ways atoms can arrange themselves in a region the size of the observable universe. It's an incomprehensibly large number, but it's finite. In an infinite universe, every one of these arrangements appears infinitely often. This means somewhere, impossibly far away, there's a region of space identical to our observable universe. Same galaxies, same stars, same planets, same Earth, same you. This isn't speculation, but a mathematical consequence of infinity, combined with finite possibilities. In fact, there are infinitely many such regions. Infinitely many identical copies of you are reading these words right now, in infinitely many identical copies of our observable universe, scattered throughout the infinite whole. These distant regions are governed by the same physical laws as our region. Physics doesn't change with location, but their specific configurations, which galaxies formed where, are independent of ours. They're causally disconnected, unable to affect us or be affected by us. As time passes and the observable universe's radius increases, we might expect to see more of the infinite whole. But cosmic acceleration complicates this. While the observable universe continues to grow, the event horizon limits how much we'll ever see. Many regions currently visible will eventually recede beyond our event horizon. In the distant future, an observer in our location would see fewer galaxies than we see today. The accelerating expansion will have carried most of them beyond the event horizon. Only nearby galaxies, bound together by gravity into our local supercluster, will remain visible. This perspective shift shows how observational cosmology depends on our cosmic epoch. We're fortunate to live when the universe is young enough that we can see the cosmic microwave background, study distant galaxies, and reconstruct cosmic history. It's a privilege we shouldn't take for granted. Infinity also raises questions about probability and meaning. In an infinite universe, everything that can happen does happen, infinitely often. Does this make individual events meaningless? If there are infinitely many copies of you, does your particular life matter? These are philosophical questions without scientific answers. Physics tells us what an infinite universe would contain, but it doesn't tell us how to value existence within it. That's a question each person must answer for themselves. What we can say scientifically is that if the universe is infinite, it's a profound fact about reality. Our observable universe would be an infinitesimal patch of an endless whole. All of human history, all our observations, all we can ever know, would describe just one tiny region of infinite space. Yet that tiny region is our home, the arena where our lives play out. Infinite or not, the observable universe is what we experience and study. Its size, 93 billion light-years across, is already incomprehensibly vast. Whether it's embedded in something larger or infinite doesn't change our immediate reality. The cosmic microwave background, or CMB, is the most important tool we have for measuring the universe's size and geometry. Understanding it helps us appreciate how scientists determine the numbers we've been discussing. The CMB is ancient light from when the universe was just 380,000 years old. Before this time, the universe was too hot for atoms to form. It was filled with ionized plasma, where electrons and atomic nuclei moved freely. This plasma was opaque to light because photons constantly scattered off free electrons. As the universe expanded and cooled, it eventually reached a temperature where electrons and nuclei could combine into neutral atoms, mostly hydrogen. This transition, called recombination, made the universe transparent. Photons could travel freely for the first time. These photons, released at recombination, have been travelling through space ever since. They fill the universe uniformly, coming from all directions. This is the cosmic microwave background we observe today. But those tiny variations are crucial. They're the seeds that grew into all cosmic structure. Galaxies, clusters, voids, the cosmic web. By studying the CMB's variations precisely, we learn about the early universe and the processes that shaped structure formation. COBE, the Cosmic Background Explorer satellite, made the first detailed measurements of CMB variations in the early 1990s. It showed the variations exist and have specific properties consistent with quantum fluctuations stretched by cosmic inflation. WMAP, the Wilkinson Microwave Anisotropy Probe, operated for 9 years starting in 2001. It mapped the CMB's variations with much higher resolution and precision. WMAP determined the universe's age, composition and geometry with unprecedented accuracy. Planck, the European Space Agency's mission, provided the most precise measurements yet, operating from 2009 to 2013. Planck's data has become the gold standard for cosmological parameters. What do these satellites measure? They map the CMB's temperature across the entire sky, creating detailed images of the ancient light. The maps show hot and cold spots, regions slightly warmer or cooler than the average 2.7 degrees. These temperature variations correspond to density variations in the early universe. Denser regions were slightly hotter, less dense regions slightly cooler. The pattern of these variations encodes information about the universe's composition, geometry and dynamics. One key feature is the acoustic peaks. Quantum fluctuations in the early universe created sound waves in the primordial plasma. These waves propagated outward at about half the speed of light, creating patterns of compression and rarefaction. When recombination occurred, these sound waves froze into the matter distribution. The largest wave had travelled a specific distance, called the sound horizon, about 450,000 light-years. This distance shows up as a characteristic angular scale in the CMB. In a flat universe, this angular scale appears as about 1 degree on the sky. In a curved universe, it would appear larger or smaller due to the curvature's lensing effect. By measuring this scale precisely, scientists determine the universe's geometry. Planck's measurements show the first acoustic peak at almost exactly the angular scale predicted for a flat universe. This is the primary evidence that the universe is flat, with curvature consistent with zero. The CMB also provides a distance ruler. We know the sound horizon's physical size from physics, about 450,000 light-years. We measure its angular size in the CMB, about 1 degree. Combining these tells us the distance to the CMB surface, about 46 billion light-years, accounting for expansion. This distance is the radius of the observable universe. It's not 46 billion light-years because light has travelled that far through stationary space, but because that's how far the CMB surface has been carried by cosmic expansion since the light was emitted. Understanding these details helps us appreciate how precisely the universe's size has been measured. It's not guesswork or rough estimation. It's based on detailed observations of ancient light, analysed using well-tested physical theories, producing measurements with small, well-understood uncertainties. The CMB is our window to the early universe and our tool for cosmic measurement. It's one of cosmology's greatest gifts, a relic from cosmic dawn that tells us about the universe's past, present, and likely future. We've established that the observable universe is 93 billion light-years across, but what lies beyond that horizon? This question probes the limits of what we can know while remaining firmly grounded in science. Beyond our cosmic horizon are regions of space that are so far away that light from them hasn't had time to reach us yet. These regions are just as real as the space we observe, governed by the same physical laws, containing galaxies and stars like those we see. What do we expect to find in these currently unobservable regions? The answer depends on a principle called the cosmological principle. The universe is homogeneous and isotropic on large scales. Homogeneous means it has the same properties everywhere. Isotropic means it looks the same in all directions. Observations strongly support this principle. The cosmic microwave background is uniform in all directions. Galaxy surveys show that while their structure on small scales, galaxies, clusters, voids, the distribution becomes increasingly uniform on larger scales. Beyond about 300 million light-years, the universe looks statistically the same everywhere. If this principle holds beyond our horizon, then the unobservable regions contain galaxies, stars, and structures similar to what we see. The specific details differ, which galaxies are where, but the overall statistical properties are the same. This is a reasonable assumption, but unproven. We can never directly verify it for regions beyond our horizon. However, inflation theory provides theoretical support. Inflation created uniform conditions throughout a region much larger than our observable universe, ensuring similar properties everywhere. There's also the question of how far beyond our horizon the universe extends. If it's finite, it must be at least 250 times larger than the observable universe, based on searches for repeated patterns in the cosmic microwave background. If it's infinite, it extends forever. An infinite universe would contain infinite variations, while any finite region would be statistically similar to our observable universe. The infinite whole would contain every possible configuration, including exact duplicates, and every variation on structure and history. Some cosmologists have tried to estimate the universe's minimum size if it's finite. Constraints from the CMB and Galaxy surveys suggest it must be at least several hundred times larger than the observable universe. Some estimates push this to thousands of times larger. But these are lower limits, not measurements. The universe could be vastly larger still, or infinite. Current observations can't distinguish between a very large finite universe and an infinite one. There's also speculation about multiverse theories, which propose that our universe is one of many, perhaps infinite universes existing in a larger multiverse. These theories arise from certain interpretations of quantum mechanics and string theory. In the multiverse context, universe means something different. Our universe would be the region affected by our particular Big Bang, which might be finite. The multiverse would be the ensemble of all such regions, possibly infinite. These ideas push beyond currently testable science into speculation. While intellectually interesting, they can't be confirmed or denied with present observations. Some scientists find multiverse theories compelling. Others dismiss them as metaphysical speculation. The debate touches on deep issues in philosophy of science. What counts as evidence? What makes a theory scientific? When does reasonable inference become unjustified speculation? Most cosmologists are comfortable making claims about unobservable regions based on the cosmological principle and inflation theory. These aren't wild guesses, but reasoned extensions of confirmed science. Still, there's humility in recognizing that ultimate verification is impossible. In the end, what lies beyond our horizon remains somewhat mysterious. We have good theoretical reasons to think it's similar to what we observe, but we can never be certain. The universe keeps some secrets, maintaining a permanent boundary between what we can know and what remains beyond reach. Understanding the universe's size requires understanding its expansion history. The universe hasn't always expanded at the same rate. Its expansion has evolved in ways that affect how we measure cosmic distances and sizes. In the first fraction of a second, the universe underwent inflation, expanding exponentially at an almost inconceivable rate. Space doubled in size every tiny fraction of a second, perhaps 60 or 70 times in total. This multiplied the universe's size by a factor of at least 10 to the 26th, possibly much more. Inflation explains why the observable universe is so large, and why it's so flat and uniform. It stretched any initial irregularities to scales far larger than we can observe, leaving us in an apparently flat, smooth patch. After inflation ended, the universe entered a more sedate expansion phase dominated by radiation. Photons, neutrinos, and other relativistic particles filled the universe, and their energy density determined the expansion rate. During this era, the universe roughly doubled in size every 50,000 years or so. As the universe expanded and cooled, matter became more important than radiation. Photons redshifted to lower energies, while matter particles maintained their mass. Eventually, matter's energy density exceeded radiation's, changing the expansion dynamics. During the matter-dominated era, which lasted several billion years, the universe's expansion gradually decelerated. Gravity, pulling on the matter, slowed the expansion. The expansion rate decreased over time, though it never stopped. Then, about 5 billion years ago, something changed. The universe's expansion began to accelerate. This acceleration is attributed to dark energy, a mysterious component that acts like anti-gravity on cosmic scales. The discovery of cosmic acceleration came in 1998 from observations of distant supernovae. Two independent teams found that these supernovae appeared dimmer than expected, indicating they're farther away than they would be in a decelerating universe. This discovery was shocking. Most cosmologists expected deceleration, not acceleration. The finding earned the Nobel Prize in Physics in 2011 for the lead researchers. Since then, many observations have confirmed acceleration. The cosmic microwave background, large-scale structure surveys, and additional supernova observations all agree. Acceleration is real, and dark energy comprises about 68% of the universe's total energy. This expansion history affects distance measurements. When we observe a galaxy at a certain redshift, its distance depends on the expansion history. If the universe decelerated more or less than expected, the galaxy would be closer or farther than simple calculations suggest. Cosmologists use models of expansion history to convert redshifts to distances. These models incorporate matter, radiation, and dark energy, each affecting expansion differently at different times. The current standard model, called lambda CDM, includes all three components. Lambda represents dark energy, the cosmological constant. CDM stands for cold dark matter. Together with ordinary matter and radiation, these components fit observations remarkably well. Lambda CDM is the concordance model, the framework most cosmologists use. With lambda CDM, we can calculate how far light has travelled from any redshift, accounting for the changing expansion rate. This gives us look-back time and co-moving distance, the standard measures used in cosmology. Look-back time is how long ago the light was emitted. For the cosmic microwave background, it's about 13.8 billion years. Co-moving distance is how far away the source is now, accounting for expansion. For the CMB, it's about 46 billion light-years. These calculations depend on knowing the expansion history, which we determine from observations. It's somewhat circular. We use expansion history to measure distances, and we use distance measurements to determine expansion history. But the circle closes self-consistently, with multiple independent observations agreeing. The expansion history also tells us about the universe's future. With dark energy dominating and driving acceleration, the expansion will continue forever, at an ever-increasing rate. The universe will become larger and colder, with galaxies spreading ever farther apart. In the far future, trillions of years from now, most galaxies will have receded beyond the event horizon. Only gravitationally bound structures, our local group of galaxies, will remain visible. The night sky will be mostly dark, with a handful of nearby galaxies the only visible objects beyond our own. Eventually, stars will exhaust their fuel, galaxies will fade, and the universe will approach a state of maximum entropy. This heat death is the likely fate of an eternally expanding, accelerating universe. It's a cold, dark future, but one that's still trillions of years away. Understanding this history helps us appreciate the universe's current size. The 93 billion light-year diameter isn't arbitrary. It's determined by the universe's age and expansion history. Different expansion histories would give different sizes. The fact that we can measure this history and calculate the size shows how far cosmology has come. A century ago, we didn't know the universe was expanding. Now we know its expansion history in detail and can predict its future evolution. To appreciate the universe's size, it helps to understand the structures within it and how they're distributed. The universe has a hierarchy of structures, from planets to galaxy superclusters, each at vastly different scales. Let's start small and work our way up. Planets range from about 1,000 to 140,000 kilometers in diameter. Earth is about 13,000 kilometers across. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. This is the typical distance between stars in our galactic neighbourhood. Stars are separated by distances millions of times their own diameters. Galaxies are vast collections of stars. Our Milky Way is about 100,000 light-years across, containing hundreds of billions of stars. Other galaxies range from dwarf galaxies a few thousand light-years across to giant ellipticals over 1 million light-years in diameter. Galaxies aren't isolated, they cluster together. The Milky Way is part of the local group containing about 100 galaxies in a region about 10 million light-years across. The two largest are the Milky Way and Andromeda, with many smaller galaxies orbiting them. The local group is part of a larger structure called the Virgo supercluster, containing thousands of galaxies in a region about 100 million light-years across. At the supercluster's heart is the Virgo cluster, a dense collection of over 1,000 galaxies. Recent surveys have revealed even larger structures. The local group and Virgo supercluster are part of Laniakea, a supercluster complex about 500 million light-years across, containing about 100,000 galaxies. Laniakea isn't the largest structure. Surveys mapping galaxy positions have found galaxy filaments stretching across over 1 billion light-years. These filaments are part of the cosmic web, the large-scale pattern of matter distribution. The cosmic web consists of dense filaments where galaxies cluster, separated by vast voids with few galaxies. The voids can be hundreds of millions of light-years across. Enormous empty regions with only scattered galaxies. This web-like structure formed through gravitational collapse of initially small density variations. Denser regions attracted more matter, growing into filaments and clusters. Less dense regions lost matter to their surroundings, becoming voids. The largest known structures are about 1 billion light-years across. Beyond this scale, the universe becomes increasingly uniform. There are no structures larger than about 1 billion light-years. At least none we've detected with certainty. These structures help us measure the universe's size and geometry. By mapping galaxies and measuring their distances, we determine the cosmic web's geometry. If the universe were curved, the web's shape would reflect that curvature. Baryon acoustic oscillations, the galaxy distribution pattern resulting from sound waves in the early universe, provide a standard ruler. The characteristic spacing of galaxies in this pattern depends on the sound horizon at recombination, about 450,000 light-years. By measuring this spacing at different distances and times, cosmologists determine the universe's expansion history and geometry. The measurements confirm flatness and agree with cosmic microwave background results. The hierarchy of structures, from planets to superclusters, spans 18 orders of magnitude in size. The observable universe is about 10 to the 9th power times larger than Earth, and about 10 to the 5th power times larger than the largest cosmic structures. This vast range of scales shows the universe's richness. At every scale, from the tiniest particles to the largest structures, there are phenomena to study and understand. The universe is layered, with complexity at every level. Understanding these scales helps us grasp the universe's size. 93 billion light-years is almost impossible to visualize, but knowing it contains billions of galaxies, thousands of superclusters, and a cosmic web with characteristic scales makes it more concrete. We're part of this hierarchy, observers on a small planet, in an ordinary galaxy, in a typical part of an enormous universe. Our scale is tiny compared to the whole, yet we've managed to map the universe from smallest to largest structures. One of the most confusing aspects of cosmic distances is the difference between light travel time and actual distance. This distinction is crucial for understanding the universe's size, so let's explore it carefully. When we observe a distant galaxy, we measure its redshift, how much its light has been stretched by cosmic expansion. From redshift, we can calculate several different distances, each meaningful in different contexts. Light travel time is how long the light has been travelling to reach us. If we observe a galaxy at redshift z equals 1, its light has been travelling for about 8 billion years. This is the look-back time. We're seeing the galaxy as it was 8 billion years ago. But in an expanding universe, this simple relationship breaks down. Light travels through space that's expanding, stretching the light's journey. By the time it arrives, the source has moved farther away than the light travel distance suggests. For nearby galaxies, the difference is small. Andromeda is about 2.5 million light-years away, and its light takes about 2.5 million years to reach us. The expansion over such short times and distances is negligible. But for distant galaxies, the difference is significant. The most distant galaxies we've observed have redshifts over z equals 10. Their light has travelled for over 13 billion years, nearly the age of the universe. But they're now over 30 billion light-years away due to expansion. The cosmic microwave background provides the extreme example. The CMB's light was emitted when the universe was 380,000 years old, about 13.8 billion years ago. But the CMB surface is now 46 billion light-years away. How can something be 46 billion light-years away if light has only been travelling for 13.8 billion years? Because space has been expanding during the journey. The CMB surface was only 42 million light-years away when the light was emitted, but expansion has carried it much farther. Understanding this distinction is essential for cosmology. When astronomers talk about distances to galaxies, they specify which distance measure they mean. Light travel time distances, co-moving distances, and other measures all appear in different contexts. For the universe's size, we use co-moving distance. The observable universe's radius is 46.5 billion light-years in co-moving distance. This is how far the CMB surface is from us now, accounting for expansion. The expansion also affects how we think about speed. Galaxies at the observable universe's edge are receding from us at about 3 times the speed of light. This sounds impossible, but it's allowed because it's space expanding, not galaxies moving through space. Special relativity says nothing can move through space faster than light, but it doesn't limit how fast space itself can expand. In an expanding universe, distant objects can recede faster than light without violating relativity. This is why we can observe objects beyond the Hubble radius, the distance where recession velocity equals light speed. Light from these objects is being carried away by expansion faster than it's approaching us, but expansion's rate decreases with time, so the light eventually makes progress and reaches us. These concepts are counterintuitive because we have no everyday experience with expanding space. On human scales, space is static. Only on cosmic scales does expansion become significant. But the mathematics is consistent and well tested. General relativity predicts these effects, and observations confirm them. The universe's expansion and the resulting distance measures are now routine parts of cosmology. When we say the universe is 93 billion light-years across, we're using co-moving distance, the proper measure for the universe's current size. This is how large the observable universe is right now, accounting for expansion that's occurred during cosmic history. The distinction between light travel time and co-moving distance shows how expansion complicates cosmic measurement. It's not as simple as multiplying light speed by time. We must account for expansion's effects, using general relativity to calculate properly. This is one reason cosmology requires sophisticated mathematics. The universe's geometry and dynamics are described by Einstein's equations, which aren't simple to solve, but solve them we have, giving us precise distances and sizes for cosmic structures. We've discussed the universe's geometry, whether it's flat, spherical, or hyperbolic. But there's another aspect to the universe's shape, its topology, how space is connected globally. This affects the universe's total size in subtle ways. Topology is about connectivity. Imagine a flat sheet of paper. You could roll it into a cylinder, connecting 2 opposite edges. The local geometry remains flat. You can't tell from small-scale measurements that you're on a cylinder, but globally the topology is different. You could also connect both pairs of opposite edges, creating a torus, like a donut surface. Again, locally flat, but globally different from an infinite plane. If you travel far enough in any direction, you return to your starting point. The universe could have similar properties. It could be globally flat, as observations suggest, but have a non-trivial topology. Space could wrap around on itself in various ways, making the universe finite even though it's flat. How do we determine the universe's topology? If the topology scale is smaller than the observable universe, we might see repeating patterns. Light could travel all the way around the universe, showing us the same galaxies from different directions. Cosmologists have searched for such patterns in the cosmic microwave background and galaxy surveys. If the universe's topology was smaller than the observable universe, we'd expect to see matching circles in the CMB or repeated galaxy positions. No definitive patterns have been found. This places lower limits on the topology scale. If the universe is finite with flat topology, it must be at least 250 times larger than the observable universe, about 23,000 billion light-years in diameter. But this is just a lower limit. The universe could be much larger, or it could be infinite with trivial topology. Current observations can't distinguish between these possibilities. There's also multiverse theories, where different universes in a multiverse might have different topologies. Our universe's topology might be somewhat arbitrary, one possibility among many, rather than uniquely determined by fundamental physics. These ideas push beyond current science into speculation. What we can say firmly is that the universe's observable geometry is flat, and its topology, if non-trivial, involves scales larger than the observable universe. For the universe's size, topology affects whether it's finite or infinite. An infinite flat universe extends forever. A finite flat universe with non-trivial topology is large but bounded, though without edges or boundaries. Both are consistent with current observations. This ambiguity is frustrating but also interesting. It shows the limits of what we can know through observation. The universe might keep some secrets, aspects of its structure that are real but forever beyond our ability to measure directly. Still, the fact that we can constrain topology at all is remarkable. Through careful observation of the cosmic microwave background and galaxy distribution, we've ruled out small topology scales. We know the universe is at least hundreds of times larger than the observable portion. This is a profound achievement. Using light from the distant past, we've measured aspects of the universe's global structure. We've reached beyond our observable horizon, albeit indirectly, to make statements about the universe as a whole. Whether the universe is finite or infinite, its topology simple or complex remains unknown. But we've narrowed the possibilities, placing rigorous constraints on what it could be. Future observations might tighten these constraints further, or we might never know for certain. Either way, we've pushed human knowledge to the cosmos's very limits. Let's pause and clearly distinguish between the observable universe and the actual universe. This distinction is central to understanding what scientists mean when they talk about the universe's size. The observable universe is the region we can see, the spherical volume around us from which light has had time to arrive. It's 93 billion light-years in diameter, containing everything we can potentially observe. 2 trillion galaxies, countless stars, all the cosmic structures we study. This is a well-defined, measured quantity. We know its size because we know the universe's age and expansion history. We can calculate how far light has travelled since the Big Bang, accounting for cosmic expansion. The result is 46.5 billion light-years in radius. The actual universe is the entire cosmos, including regions beyond our observable horizon. Its size is unknown and possibly unknowable. It could be just slightly larger than the observable universe, vastly larger or infinite. This distinction matters because when people ask how big is the universe, they might mean either quantity. The observable universe has a definite size. The total universe's size is uncertain. Scientists have measured the observable universe precisely. The 93 billion light-year figure is not speculation, but calculation based on well-established physics and careful observations. When scientists say they've measured the universe's size, this is what they mean. But the popular question quote 3 often means the total universe. And for that, we don't have a definite answer. We have lower limits, saying it must be at least a certain size. We have theoretical arguments suggesting it might be infinite. But we don't have a measurement of total size. The event horizon, about 16 billion light-years away, is the boundary beyond which we'll never see anything, even waiting forever. Light emitted from beyond this distance today will never reach us, because space between us and the source is expanding too fast. So while the observable universe continues to grow, approaching but never quite reaching the event horizon, the portion of the total universe we'll ever observe is limited. Many regions exist that we'll never see, even given infinite time. But philosophically and scientifically, the total size matters. If the universe is finite, it raises questions about what, if anything, lies beyond its boundaries. If it's infinite, it raises questions about infinity's implications, including infinite duplicates and every possible configuration occurring infinitely often. These questions can't be fully resolved with current observations. We can constrain the total universe to be much larger than the observable portion, but we can't determine if it's finite or infinite. This limitation is fundamental, arising from the finite speed of light and the finite age of the universe. Some scientists find this limitation frustrating. Others find it philosophically interesting. A boundary between what can be known empirically and what requires theoretical reasoning. It's a place where science meets philosophy, where observation ends and inference begins. The distinction between observable and actual also appears in other contexts. We observe only a tiny slice of cosmic history from recombination to now. The universe existed before we can observe, and it will exist after we're gone. Similarly, we observe only a fraction of space, while much more likely exists beyond our horizon. In both cases, time and space, we're limited observers seeing only part of the whole. But through physics and reasoning, we can infer much about the parts we can't see. We can't observe the first 100,000 years after the Big Bang directly, but we can reconstruct what happened. Similarly, we can reason about regions beyond our horizon using the cosmological principle. This interplay between observation and inference is fundamental to cosmology. Unlike laboratory sciences where we can manipulate and control experiments, cosmology must work with the universe as given. We can only observe, we can't experiment. So inference from limited data, guided by theory, becomes essential. The measurement of the universe's size shows this interplay. The observable universe's size is measured. The total universe's size is inferred to be much larger, possibly infinite, based on geometry, topology, and theoretical considerations. Both kinds of knowledge, observational and inferential, contribute to our understanding. Understanding the universe's size isn't just an abstract exercise. It has profound implications for cosmology, physics, and our understanding of reality itself. Let's explore why size matters and what it tells us. First, size constrains the universe's geometry and topology. A small universe must have positive curvature or non-trivial topology. A flat, infinite universe is the simplest possibility for the large size we observe. The fact that the universe is at least hundreds of times larger than the observable portion supports flatness and possibly infinity. Size also affects our understanding of cosmic inflation. Inflation predicts the universe should be flat and much larger than the observable portion. Observations confirming this support inflation theory. If the observable universe had significant curvature or small topology, it would challenge inflation. Size matters for understanding structure formation. The largest structures we observe are about 1 billion light-years across. This is tiny compared to the observable universe's 93 billion light-year diameter. The size difference shows that structure formation operates on scales much smaller than the universe as a whole. If the universe was smaller, large structures might be affected by boundary effects or topology. The fact that it's so large means structures form in essentially infinite space, with no edge effects. This simplifies theoretical models and confirms the cosmological principle on large scales. Size also affects probability and uniqueness. In a small universe, there might be only one of each type of galaxy, star system, or planet. In a large or infinite universe, every type appears many or infinitely many times. This affects how we think about our place in the cosmos. An infinite universe contains infinite instances of everything possible. Every unlikely event occurs infinitely often. This challenges intuitions about probability and uniqueness developed in finite contexts. Size matters for the universe's future. In a finite universe, matter and energy are limited. In an infinite universe, they're unlimited. This affects long-term scenarios like heat death or eternal recurrence. The universe's ultimate fate depends partly on whether it's finite or infinite. Size also constrains quantum cosmology, theories attempting to describe the universe's creation quantum mechanically. Different quantum theories predict different size distributions. Observations of actual size can test these theories. For instance, some quantum cosmology models predict the universe should be small, just barely larger than the observable portion. Others predict it should be infinite with high probability. The observation that the universe is at least hundreds of times larger than observable helps discriminate between models. For example, measuring the universe's geometry requires observing scales comparable to the observable universe's size. If it was smaller, we couldn't constrain curvature as precisely. The large size allows precision measurements of cosmological parameters. Size also affects how we think about time and causality. Regions beyond our particle horizon can't have affected us causally, because not enough time has passed for signals to propagate. The universe's large size means vast regions are causally disconnected from us. This raises questions about initial conditions. If distant regions couldn't communicate, how did they come to have similar properties? Inflation provides an answer. They were in causal contact before inflation, then stretched to causally disconnected distances. Finally, size matters for the search for life. A larger universe means more planets, more opportunities for life to arise. If the universe is infinite, life must exist elsewhere, probably infinitely many times. If it's large but finite, life is likely but not certain to exist elsewhere. The implications of size ripple through cosmology and physics. It's not just a number, but a fundamental property affecting our understanding of the universe's origin, evolution, structure, and fate. Measuring size, or at least constraining it, is one of cosmology's essential tasks. That scientists have determined the observable universe's size precisely and place strong lower limits on the total universe's size represents a profound achievement. We've measured the cosmos, understood its vast scale, and begun to grasp what that scale implies. The question of the universe's size connects to one of the most speculative ideas in modern cosmology, the multiverse. While this pushes beyond established science, it's worth exploring because it changes how we think about size. The multiverse hypothesis proposes that our observable universe is just one of many, perhaps infinitely many, separate universes. These other universes might have different properties, different physical laws, or different initial conditions. There are several multiverse concepts, arising from different theoretical frameworks. Understanding them helps clarify what universe means in different contexts. The Level 1 multiverse, proposed by cosmologist Max Tegmark, is simply the extension of our own universe beyond our observable horizon. If the universe is infinite, as observation suggests might be the case, then there are infinitely many regions like our observable universe, each causally disconnected from the others. These bubbles might have different values for physical constants, different numbers of dimensions, different particle physics. Each bubble is causally disconnected from others, making them separate universes in a practical sense. This Level 2 multiverse is more speculative than Level 1. It depends on eternal inflation being real, which isn't proven. But eternal inflation arises naturally in many inflation models, making it plausible if inflation is real. The Level 3 multiverse involves quantum mechanics' many worlds interpretation. This proposes that every quantum measurement splits reality into branches, each one representing a different measurement outcome. All branches are equally real, existing in a vast multi-dimensional configuration space. In this picture, our universe is one branch among infinitely many. Other branches contain different versions of history, different outcomes of quantum events. All are part of a larger multiverse structure. This interpretation is philosophically controversial. Many physicists prefer other quantum interpretations without multiple worlds, but some find many worlds elegant and take it seriously. The Level 4 multiverse, Tegmark's most speculative proposal, suggests that every mathematically consistent structure exists physically somewhere. All possible mathematical universes are real, existing in some abstract mathematical space. Our universe would be one mathematical structure among all possibilities. Other structures, with completely different mathematics, physics, and logic, would also exist as separate universes. This is highly speculative. More philosophy than physics, there's no way to test it observationally. But it raises interesting questions about the relationship between mathematics and physical reality. For our discussion of size, multiverse theories change what universe means. In Level 1, our universe is infinite, and other universes are just distant regions of the same space. Size is infinite, end of story. In Level 2, our universe is the bubble we're in, perhaps finite and measurable in principle. The multiverse as a whole might be infinite with infinite bubbles, but each individual universe has its own size. In Levels 3 and 4, size becomes even more ambiguous. What does size mean for a branch of quantum mechanics or an abstract mathematical structure? These multiverses exist in configuration space or mathematical space, not physical space. Most scientists are skeptical of multiverse theories, at least the more speculative versions. Level 1 is simply a consequence of infinity, and isn't controversial among those who accept the universe might be infinite. Level 2 has some theoretical support from inflation, but isn't proven. Levels 3 and 4 are more philosophical, interpretations or speculations rather than established science. They might be true, but they're not testable with current methods, pushing them beyond what many consider science. Still, multiverse ideas are discussed seriously in theoretical physics. They arise naturally from certain theories and interpretations. Some phenomena, like the fine-tuning of physical constants for life, seem easier to explain in a multiverse context. The Multiverse Connection shows how the size question links to deep issues in physics and philosophy. It's not just about measuring distance, but about understanding what exists, how much of it there is, and what constitutes a universe versus a multiverse. Science has measured the observable universe precisely, and constrained the total universe's size significantly. But there are limits to what we can know. Some questions about the universe's size might be forever beyond our reach. We can never directly observe beyond our cosmic horizon. This is a fundamental limit, not a technological one. Even with arbitrarily advanced telescopes, we can't see regions from which light hasn't had time to reach us. As the universe ages, the horizon expands, potentially allowing us to see more. But accelerating expansion creates an event horizon that limits what we'll ever observe. Many regions will forever remain beyond our view. This means we can never confirm the universe's total size through direct observation. If it's infinite, we can never survey all of it. If it's finite but larger than the maximum observable volume, we can never see its boundaries. We can make inferences. If the universe has small topology, we might detect repeated patterns indicating we're seeing the same structures from different angles. If it has curvature, we might measure that curvature and calculate the universe's total size in closed geometries. But if the universe is flat and larger than the eventually observable volume, its total size remains unknown. We can place lower limits, saying it must be at least a certain size, but we can't determine the actual size. This is a permanent ignorance, not temporary. No future technology can overcome it because it's limited by light speed and cosmic expansion. These are fundamental constraints, not practical ones we might someday engineer around. Some scientists find this limitation frustrating. Science seeks complete understanding, yet the universe withholds information about its own extent. We can know much, but not everything. Others find it philosophically interesting. It shows that reality extends beyond observable reality. There are facts about the world that are true but unknowable through empirical observation. This raises questions about the nature and limits of scientific knowledge. What does it mean to quote 7 something we can't observe? If we infer based on observed regions that distant regions are similar, applying the cosmological principle, does that count as knowledge? Or is it merely well-reasoned speculation? Different philosophical positions give different answers. Empiricists might say knowledge requires observation, so we can't know about unobservable regions. Rationalists might say logical inference from observed patterns constitutes knowledge even without direct observation. Most scientists take a pragmatic middle ground. Inferences based on well-established principles like homogeneity and isotropy are treated as knowledge, though with appropriate humility about limitations. There are also questions about the universe's initial conditions that might be unanswerable. Why did the universe start with the properties it has? Why this particular size, curvature, expansion rate? These might have no deeper explanation, simply being brute facts about reality. Or they might be explained by a deeper theory, perhaps quantum cosmology or string theory. But even those theories might have arbitrary elements, parameters that must be observed rather than predicted. This leads to an infinite regress. Each theory might rest on assumptions that could be explained by a deeper theory, which rests on further assumptions. At some level, we might encounter facts that simply are, with no further explanation available. The universe's size might be such a fact. Perhaps it's infinite because the laws of physics make infinity natural. Perhaps it's finite with a specific value determined by quantum cosmology. Or perhaps it's arbitrary, a random outcome of quantum fluctuations in the early universe. We might never know which. Even if we develop sophisticated theories that appear to predict the universe's size, we'd still wonder if those theories are truly fundamental or rest on deeper principles yet to be discovered. This uncertainty is part of science. Complete certainty is rare. We work with the best current understanding, knowing it might be revised as observations and theories improve. There's also the question of whether unobservable properties are meaningful. If the universe's size beyond our horizon has no observable consequences, does it matter what that size is? Is it even a meaningful question? Some philosophers say no. They argue that science should concern itself only with observable phenomena. Speculation about unobservable regions is metaphysics, not physics. Others maintain that the universe's actual properties, observable or not, are facts worth contemplating. The universe has whatever size it has, regardless of what we can observe. This debate won't be resolved soon. It's a long-standing philosophical question about the relationship between reality and observation, between what exists and what we can know. For practical cosmology, the focus is on what can be measured. The observable universe's size, the constraints on curvature and topology, the limits on how large or small the total universe might be, these are all within science's domain. Beyond that, into questions about infinite space, unobservable regions, and the ultimate nature of reality. We enter territory where observation provides limited guidance. Theory, mathematics, and philosophy must carry more weight. We observe what we can, infer what we reasonably can, and accept that some mysteries might persist. That's the nature of being finite observers in a possibly infinite universe. Beyond the numbers and measurements, what does the universe's vast size mean? How should we think about inhabiting such an enormous cosmos? Let's contemplate the implications of cosmic scale. 93 billion light-years across. This number is so large it loses meaning. We can't visualize it, can't hold it in our minds. The largest distance we can intuitively grasp is perhaps the size of Earth, maybe the distance to the Moon. Beyond that, numbers become abstract. Yet this scale is real. The universe truly is this vast. Light travelling at the fastest possible speed for 93 billion years would cross the observable universe. That's not metaphor or exaggeration, but measured fact. One way to appreciate the scale is through ratios. An atom is to a human as a human is to a large mountain. Earth is to the Sun as the solar system is to the distance to the nearest star. Each step increases size by factors of thousands or millions. The observable universe is about 10 to the 26th meters across. A human is about 1 meter. The ratio is 10 to the 26 to 1. This is the same as comparing a human to something 10 to the negative 26 meters, far smaller than an atom, approaching the Planck scale where quantum gravity becomes important. We exist between these extremes, larger than the quantum realm, smaller than the cosmic realm, by almost incomprehensible factors. Our scale is arbitrary from a cosmic perspective, neither large nor small, but somewhere in between. The universe's size also affects how we think about significance. In such vast space, Earth is tiny, invisible from across the galaxy, let alone the universe. Everything we've done, all of human history, occurs on a speck in a vast cosmos. This can feel diminishing. Carl Sagan's pale blue dot meditation captures this. Looking at Earth from across the solar system, seeing it as a single pixel in a sunbeam, reflecting on how all human concerns play out on that tiny stage. From the universe's perspective, if it had one, we're negligible. The universe was here billions of years before us and will be here billions of years after. Our presence or absence makes no difference to cosmic evolution. But another perspective is possible. Yes, we're small, but we're also remarkable. We're matter that has become conscious, able to contemplate the universe that created us. We're the universe knowing itself, at least in this small corner of space. Our significance isn't in physical size, but in consciousness and understanding. The universe might be vast, but as far as we know, only a tiny fraction of it is aware of itself. We might be rare, possibly unique, in our ability to measure and comprehend cosmic scale. This perspective grants meaning despite size disparity. We matter not because we're large, but because we can think, feel, wonder, and understand. These capacities aren't diminished by the universe's vastness. The scale also invites humility. We're newcomers to a very old universe, residents of a tiny planet in a vast cosmos. Our knowledge, though impressive, is limited. We see only a fraction of what exists, understand only part of how it works. This humility is healthy. It prevents arrogance, the belief that we've figured everything out. The universe is deeper and larger than our current understanding. There's always more to learn, more to discover. Yet humility can coexist with pride in achievement. We have measured the observable universe. We understand cosmic expansion. We've calculated distances and sizes across billions of light years. This is extraordinary for a species that only recently learned the Earth orbits the Sun. The scale also affects how we think about time. The universe is 13.8 billion years old. Recorded human history is about 5,000 years. All of civilization, all our religions, empires and achievements occupy about 0.036% of cosmic history. We're latecomers. The universe existed for over 9 billion years before Earth formed. Stars were born and died, galaxies merged and evolved, long before our planet existed. If cosmic history were compressed to a year, humans would appear in the last few minutes. Yet here we are, conscious in this moment, aware of our place in time and space. Our brief existence allows us to contemplate the vast reaches of space and time. That seems meaningful, even if we're small and temporary. The scale might also affect how we think about life elsewhere. In a universe this large, with billions of galaxies each containing billions of stars, many with planets, it seems unlikely we're alone. The numbers favour life arising elsewhere. If the universe is infinite, life must exist elsewhere, probably infinitely many times. Even if life is rare, infinity makes it abundant. If the universe is merely very large, life is probable though not certain. This changes our cosmic context. We might not be unique, but one instance of life among many. Other civilizations might be contemplating the same cosmic scales, asking the same questions about size and significance. Or perhaps we're alone, life being so rare that despite vast numbers of planets, it arose only here. This would make us uniquely precious. The only place in the universe where matter has become conscious. How we integrate that knowledge into our lives, what meaning we derive from cosmic scale, is up to each of us. The universe provides the facts, we provide the meaning. To appreciate how we've measured the universe's size, it helps to understand the history of cosmic measurement, how we've gradually determined larger and larger distances, culminating in measuring the observable universe itself. Ancient astronomers had no concept of cosmic scale. The Earth seemed vast, the heavens mysterious. The stars were thought to be on a celestial sphere just beyond the planets, all at the same distance. The universe was small by modern standards, perhaps just our solar system. The first accurate distance measurement was to the moon. Ancient Greeks used geometry, observing how the moon's position against stars differs when viewed from different locations on Earth. By the 3rd century BCE, distances to the moon and sun had been roughly estimated, but stellar distances remained unknown until the 19th century. Stars are so distant that their parallax, the shift in position as Earth orbits the sun, is tiny, too small to measure with naked eye or early telescope observations. In 1838, Friedrich Bessel finally measured the first stellar parallax, determining that the star 61 Cygni is about 11 light-years away. This opened astronomy to the stars, allowing distance measurements beyond the solar system. Over the following decades, parallax measurements accumulated, but the technique only works for relatively nearby stars, within about 100 light-years with 19th century methods. More distant stars required different techniques. Variable stars provided the next breakthrough. Henrietta Leavitt's work on Cepheid variables in the early 1900s showed that these stars' periods and luminosities are correlated. Longer period Cepheids are intrinsically brighter. By measuring a Cepheid's period and apparent brightness, its distance can be calculated. Edwin Hubble used Cepheids in the 1920s to measure distances to nearby galaxies, proving they're outside the Milky Way. This expanded the cosmic distance scale enormously, from thousands of light-years to millions. Hubble also discovered cosmic expansion, finding that distant galaxies recede faster than nearby ones, with velocity proportional to distance. This Hubble's law provided a way to estimate distances to very distant galaxies from their redshifts. But calibrating Hubble's constant, the proportionality factor between distance and velocity, required accurate distance measurements to nearby galaxies. This became a major effort spanning decades. Various methods were developed. Type Ia supernovae as standard candles, the Tully-Fisher relation between galaxy luminosity and rotation speed, the Faber-Jackson relation for elliptical galaxies. Each method extended the distance ladder farther. By the late 20th century, astronomers could measure distances to galaxies billions of light-years away. Observations of the cosmic microwave background provided the distance to the surface of last scattering, about 46 billion light-years in comoving distance. The Hubble Space Telescope's Key project, operating through the 1990s, aimed to measure Hubble's constant to 10% accuracy. It succeeded, determining that galaxies recede at about 70 kilometers per second per megaparsec. But tensions emerged. Different methods gave slightly different values for Hubble's constant. Ground-based measurements using supernovae suggested one value. Cosmic microwave background observations from Planck suggested another, about 9% lower. This Hubble tension persists today. Either some measurements have systematic errors, or there's new physics affecting cosmic expansion at different times and scales. Resolving this tension is a major goal of current cosmology. Despite this tension, the observable universe's size is well determined. It depends more on the universe's age, which is precisely known from the cosmic microwave background, than on Hubble's constant. The 46.5 billion light-year radius is secure to within a few percent. The history shows how cosmic measurement advanced through a series of distance ladders. each rung allowing us to reach farther. Parallax to nearby stars, Cepheids to nearby galaxies, supernovae to distant galaxies, cosmic microwave background to the universe's edge. Each method had to be carefully calibrated using closer methods. The entire ladder's reliability depends on the first rungs being accurate. Errors propagate and amplify, so precision at each level is crucial. Modern missions continue refining measurements. Gaia, a European satellite, is measuring parallaxes for over 1 billion stars with unprecedented precision. Future surveys will measure distances to billions of galaxies. The cosmic distance ladder continues to be reinforced. The measurement of the observable universe's size represents the culmination of this centuries-long effort. From Bessel's first stellar parallax to Planck's cosmic microwave background maps, astronomers have pushed distance measurements from light-years to billions of light-years. This is one of humanity's great intellectual achievements, determining the scale of the cosmos through patient observation and clever reasoning. We've measured the immeasurable, quantified the vast, mapped the universe from Earth to the cosmic horizon. The precision is remarkable. We know the observable universe's diameter to about 93 billion light-years, with uncertainties of just a few percent. This isn't guesswork, but rigorous measurement, as reliable as any in science. Future observations will refine this further. Better measurements of Hubble's constant, more precise cosmic microwave background data, improved understanding of dark energy, all will sharpen our knowledge of cosmic scale. But the basic achievement is complete. We've measured the universe's observable size. It's a testament to human curiosity, ingenuity, and persistence, a lasting contribution to human knowledge. Cosmic inflation plays a central role in explaining the universe's size and properties. Understanding inflation helps us appreciate why the universe is as large as it is, and why measuring its size reveals what it does. Inflation theory was proposed in the early 1980s by Alan Guth and others to solve several puzzles in cosmology. Why is the universe so flat? Why is it so uniform? Why don't we observe certain exotic particles predicted by particle physics theories? Inflation proposes that in the first tiny fraction of a second, about 10 to the negative 35 seconds after the Big Bang, the universe underwent exponential expansion. Space doubled in size every 10 to the negative 37 seconds or so, continuing for perhaps 10 to the negative 32 seconds. Inflation also explains the universe's uniformity. Before inflation, the universe was small enough that different regions could reach thermal equilibrium. Inflation then stretched these causally connected regions to opposite sides of the observable universe, preserving their similarity. For the universe's size, inflation has profound implications. It suggests the universe is vastly larger than the observable portion, perhaps by factors of 10 to the 26 or more. The entire universe might be to the observable universe, as the observable universe is to an atom. Or inflation might have created an infinite universe. If inflation expanded a finite initial region to infinite size, as some models suggest, the universe would be infinite. In this picture, the observable universe is an infinitesimal patch of an infinite whole. Inflation also connects to the multiverse idea. In eternal inflation scenarios, inflation never completely ends but continues in some regions while ending in others. Each region where it ends becomes a potentially with different properties. These bubbles, if they exist, are causally disconnected from each other, making them separate universes in a practical sense. The total inflated space might be infinite, containing infinite bubbles, each large or infinite in its own right. Inflation is supported by several observations. The cosmic microwave background's flatness and uniformity match inflation's predictions. The pattern of temperature fluctuations matches predictions from quantum fluctuations stretched by inflation. Some inflation models predict gravitational waves from the inflationary epoch. These might leave a signature in the cosmic microwave background's polarization. Several experiments are searching for this signature, though none have detected it yet. Not all cosmologists accept inflation. Some argue it's too flexible, able to explain almost any observation. Others propose alternative theories to solve the same puzzles inflation addresses. But inflation remains the leading explanation for the universe's flatness, uniformity, and large size. It's the framework most cosmologists use when thinking about the early universe and cosmic origins. For measuring the universe's size, inflation provides context. The observable 93 billion light-years is just what we can see of a region created during inflation. The total size depends on how long inflation lasted and how fast space expanded. If inflation lasted just long enough to solve the flatness and horizon problems, the universe needs to be only about 1,000 times larger than the observable portion. If it lasted longer, as many models suggest, the universe could be vastly larger or infinite. We can't observe beyond our horizon to test this directly, but inflation's success in explaining observed properties gives us confidence that the universe is indeed much larger than what we see. Inflation also suggests that measuring the observable universe's size, curvature, and composition tells us about the initial conditions from which inflation started. The observable universe's properties reflect the quantum state that underwent inflation. This means studying the cosmic microwave background and large-scale structure isn't just measuring the universe now, but probing the physics of the inflationary epoch, 10 to the negative 35 seconds after the Big Bang. It's remarkable that we can learn about such early times through observations of the present universe. Inflation remains an active research area. Modified inflation models are proposed regularly. Connections to string theory and quantum gravity are being explored. Future observations might distinguish between different inflation scenarios. For our understanding of size, inflation explains why the universe is large, flat, and uniform. It predicts the universe extends far beyond our horizon, and it connects the observable universe's measured properties to fundamental physics at the earliest moments. Inflation is the bridge between quantum physics at the smallest scales and cosmology at the largest. It explains how the universe grew from microscopic to cosmic, from quantum fluctuations to galactic structures. Understanding inflation is essential to understanding size. We've discussed limits to what we can observe, but let's think more carefully about these limits and what they mean for measuring the universe's size. There are several different horizons and boundaries worth understanding. The particle horizon is the boundary beyond which events couldn't have affected us because light hasn't had time to travel from there. It's the edge of the observable universe, currently at a moving distance of about 46.5 billion light-years. This horizon grows as the universe ages. Light from slightly farther regions reaches us, expanding our observable volume. In principle, we'll eventually observe more of the universe, though acceleration limits how much more. The Hubble radius is the distance at which recession velocity equals light speed due to cosmic expansion. It's currently about 14.4 billion light-years. Objects beyond this recede faster than light, though we can still observe them. This seems paradoxical, but isn't. Objects can recede faster than light without violating relativity, because it's space expanding, not objects moving through space. Photons from these objects make progress toward us despite the expansion, because expansion's rate decreases with time. The Hubble radius is not the observable universe's boundary. We can observe objects beyond it because they emitted light when they were closer, and expansion was faster. The observable universe extends well beyond the Hubble radius. The event horizon is the boundary beyond which events occurring now will never be observable, even with infinite patience. It's caused by accelerating expansion. Light emitted from beyond this distance will never catch up to us because space between us and the source is expanding too fast. There are also practical limits beyond fundamental ones. Faint objects are hard to detect. Distant galaxies might be too dim for our telescopes, even if they're within the observable universe. Cosmic variance, random fluctuations in structure, limits how well we can measure certain properties. Our location in one particular region also limits what we can observe about global topology. If the universe has non-trivial topology larger than the observable universe, we can't detect it directly, though we might constrain it statistically. These limitations affect how precisely we can measure cosmic properties. The observable universe's size is well determined, but the total universe's size is constrained only to be much larger than observable, with no upper limit. For some properties, we must extrapolate from observed regions to the unobservable universe using the cosmological principle. This is reasonable but involves assumptions that can't be directly verified. There's also the question of whether the laws of physics are the same everywhere. We assume they are, and observations support this within the observable universe. But in principle, different regions might have different physics. Inflation suggests physics should be uniform over regions much larger than observable, because all regions started from similar quantum states. But if eternal inflation creates bubble universes, different bubbles might have different physics. These speculations highlight the limits of empirical knowledge. We can observe only a finite region and infer properties of the unobservable universe. Some inferences are well supported by theory and observation, others are more speculative. The limits of observation also affect the universe's fate predictions. We observe accelerating expansion now and extrapolate that it will continue. But if dark energy's properties change in the future, expansion might decelerate or even reverse. We can't observe the future directly. We must rely on models of dark energy based on current observations. If those models are wrong, our predictions about the universe's ultimate fate might be too. Despite these limits, we've achieved remarkable observational reach. We observe galaxies billions of light years away, seeing them as they were billions of years ago. We map the cosmic microwave background from when the universe was 380,000 years old. We constrain the universe's properties from fractions of a second after the Big Bang. This reach far exceeds what might have seemed possible. A century ago, we didn't know galaxies existed beyond the Milky Way. Now we observe galaxies near the edge of the observable universe and infer properties of regions far beyond. Future observations will push some limits farther. Better telescopes will detect fainter, more distant objects. Better measurements will refine cosmic parameters. Better theories might allow us to infer more about unobservable regions, but fundamental limits will remain. Light speed and cosmic expansion ensure we can never observe infinitely far. The event horizon limits what we'll ever see. Some aspects of the universe might remain forever beyond our reach. Accepting these limits is part of doing cosmology. We work with the universe as observable, inferring what we can about the unobservable, and acknowledging uncertainty where it exists. The universe's size is partly measured, partly constrained, and partly unknown, depending on what aspect we're asking about. This mix of knowledge and ignorance is typical in science. Complete knowledge is rare. We work with what we can observe and reasonably infer, accepting that some questions might remain unanswered. The limits of observation remind us of our position. We're observers at one location in space and time, seeing what light and other signals can reach us. The universe extends beyond our view, real but inaccessible, an eternal mystery at the edge of knowledge. Beyond the science, measuring the universe's size raises philosophical questions about knowledge, reality, and our place in existence. Let's contemplate these deeper implications. One question is epistemological. How can we claim to know things we can't observe? The total universe's size might be beyond our horizon, forever unobservable, yet we make claims about it based on inference. Is this genuine knowledge or mere belief? Philosophy of science distinguishes between observation and inference. Observation is direct empirical access. Inference is reasoning from observations to conclusions about unobserved phenomena. Science uses both, but they carry different epistemic weight. Observation is more certain. We trust what we directly measure more than what we infer. But inference can also be reliable if it's based on well-established principles and rigorously tested theories. Claiming the universe is flat based on cosmic microwave background observations is reliable inference. We directly observe the CMB's properties and infer flatness from those properties using general relativity, a well-tested theory. Claiming the universe is much larger than the observable portion is similarly reliable. It follows from flatness and the absence of topology signatures in the CMB. While less certain than direct observation, it's well supported. This position is controversial. It seems anthropocentric to tie existence to human observability. The universe existed before observers and would exist if all observers disappeared. Existence is independent of observation. But the counter-argument is that science should restrict itself to empirically testable claims. Metaphysical speculation about unobservable regions might be intellectually interesting, but isn't science. Most cosmologists ignore this debate and proceed as realists. They treat the unobservable universe as real, making claims about it based on extrapolation from observed regions. This practical approach has been fruitful. There's also the question of uniqueness. If the universe is infinite with infinite instances of every possible configuration, are you unique? Or are there infinite copies of you? This challenges intuitions about identity and individuality. We think of ourselves as unique individuals, but in an infinite universe, uniqueness becomes problematic. There are infinitely many configurations indistinguishable from you. Some philosophers find this troubling, others accept it as a consequence of infinity. Still others argue it's meaningless because the copies are causally disconnected, unable to interact. The question of meaning also arises. Does the universe's vast size make individual existence meaningful or meaningless? Are we significant or insignificant in cosmic context? This is perhaps more psychological than philosophical. Some find cosmic scale diminishing, making human concern seem trivial. Others find it inspiring, making our existence seem miraculous. From a philosophical perspective, meaning isn't something the universe provides, it's something conscious beings create. The universe doesn't care about our existence, but that doesn't make our existence meaningless. We create meaning through our choices, relationships, and values. Cosmic scale doesn't diminish this. Our lives matter to us and to those we affect, regardless of how large the universe is. There's also the question of purpose. Does the universe have a purpose? Did it come into existence for any reason? Is there teleology, goal-directedness, in cosmic evolution? Science doesn't address purpose. It describes how things are and how they change, not why they exist or what they're for. Purpose questions are outside science's scope, belonging to philosophy or religion. But the universe's properties, including its size, affect how we think about purpose. A small, young universe might suggest creation for specific aims. A vast, ancient universe suggests no particular purpose, just physical law playing out. These implications are personal. Each person must decide what the universe's size means for their worldview. Science provides facts. Individuals provide interpretation and meaning. Understanding the universe's size is a scientific achievement. Deciding what that understanding means for human existence, knowledge and purpose is a philosophical and personal task. Both are valuable. Science expands knowledge of the physical world. Philosophy and personal reflection integrate that knowledge into our understanding of ourselves and our place in reality. The universe is 93 billion light-years across as far as we can observe, possibly much larger beyond our horizon. This is a fact. What it means is up to us. Looking forward, how will our understanding of the universe's size evolve? What future observations and theories might refine or revise our knowledge? Let's contemplate what's next in cosmic measurement. New telescopes will push observational limits. The James Webb Space Telescope, launched in 2021, observes in infrared, seeing farther and earlier than Hubble. It's already detecting galaxies from when the universe was just a few 100 million years old. Closer to the Big Bang than ever observed before, Webb will refine measurements of cosmic expansion, potentially resolving the Hubble tension. Its observations of distant supernova and galaxies will improve distance measurements and test dark energy models. Gravitational wave astronomy offers new windows on the universe. LIGO and Virgo detect gravitational waves from merging black holes and neutron stars. Future space-based detectors like LISA will observe different sources, including mergers of supermassive black holes. Gravitational waves from the early universe, potentially from inflation, might be detectable. These would provide independent information about cosmic history and the universe's size and evolution. Improved cosmic microwave background measurements will continue. Ground-based and balloon-borne experiments are mapping the CMB's polarization with increasing precision. Future satellites might follow Planck, measuring the CMB even more accurately. These observations will tighten constraints on the universe's curvature, potentially determining whether it's exactly flat or has tiny curvature. They'll measure the cosmological parameters, including dark energy properties, with percent or sub-percent precision. Massive galaxy surveys will map billions of galaxies, tracing the cosmic web structure in unprecedented detail. The Dark Energy Survey, the Vera Rubin Observatory's legacy survey of space and time, and other projects will create three-dimensional maps spanning billions of light-years. These surveys will measure baryon acoustic oscillations, the pattern in galaxy distribution from early universe sound waves. This provides an independent standard ruler for measuring cosmic expansion and geometry. Theoretical work will also advance. Better understanding of dark energy, dark matter, and cosmic evolution will improve models. Connections to particle physics and quantum gravity might provide new insights. Inflation theory will be refined and tested. Different inflation models make slightly different predictions. Precise observations might distinguish between them, narrowing the range of viable theories. Quantum cosmology, attempting to describe the universe's creation quantum mechanically, might mature. Currently speculative, quantum cosmology could eventually make testable predictions about the universe's initial conditions and properties. String theory, if it's correct, might constrain the universe's properties, including its size and topology. Different string theory compactifications produce different cosmic properties. Observations might help select which compactification describes our universe. Artificial intelligence and machine learning will aid analysis. Vast data sets from surveys require sophisticated algorithms to extract information. AI can identify patterns humans might miss. Finding subtle signals in noisy data. Citizen science will contribute. Projects like Galaxy Zoo have shown that volunteer astronomers can help classify and analyze cosmic objects. Future projects will likely engage even more public participation. Despite all these advances, some questions might remain unanswered. The universe's total size, if it exceeds the eventually observable volume, might never be determined. The question of finite versus infinite might persist indefinitely. This uncertainty is acceptable. Science doesn't require complete knowledge. Progress consists of improving understanding, refining measurements, testing theories. Complete certainty is rare and perhaps unnecessary. Future discoveries might also surprise us. Every major advance in observational capability has revealed unexpected phenomena. New telescopes and detectors will likely find things we haven't predicted. These surprises drive scientific progress. They challenge our understanding, forcing us to revise theories and develop new ideas. The history of cosmology is full of surprises, from cosmic expansion to dark energy. The universe's size might change in unexpected ways. If dark energy's properties evolve, the future expansion might differ from predictions. The observable universe might grow faster or slower than expected. Or we might discover the observable universe is smaller than thought if some systematic error biased current measurements. This seems unlikely given how many independent observations agree, but it's possible. More likely, measurements will be refined, errors reduced, and understanding deepened. The 93 billion light-year figure might be adjusted slightly, but probably won't change dramatically. It's a robust result from well-tested methods. The total universe's size will remain more uncertain. We'll likely improve lower bounds, saying it must be at least such and such size, but determining actual size might remain beyond reach. Future civilizations, if any exist trillions of years from now, will face different observational challenges. The accelerating expansion will have carried most galaxies beyond their event horizon. They'll see only nearby galaxies, making cosmology much harder. They might not discover cosmic expansion, or the Big Bang from direct observation. They'd need to rely on preserved knowledge from earlier epochs, or make inferences from limited data. This thought shows we're fortunate to live when we do. The universe's age and expansion rate are such that we can observe a rich cosmic history. A few billion years earlier, and we'd see less structure. A few trillion years later, and we'd see far less. We're in a brief window, cosmically speaking, when the universe reveals much of its nature. Future measurements will exploit this window, learning as much as possible while observations remain rich. The future of cosmic measurement is bright. New tools, new methods, new ideas will refine our understanding. The universe's size, already measured to reasonable precision for the observable portion, will become known even better. And the quest will continue, humans asking ever deeper questions, pushing against the boundaries of knowledge, seeking to understand the cosmos that contains us. This drive for understanding is eternal, as long as consciousness exists to wonder and explore. As we enter these final contemplative chapters, let's think about the personal dimension. How the universe's vast size relates to you as an individual living in this enormous cosmos. You exist in a specific location in the universe. You're on Earth, third planet from the Sun, in a solar system orbiting 26,000 light-years from the centre of the Milky Way galaxy. Your galaxy is part of the local group, which is part of the Virgo supercluster, which is part of Laniakea. This cosmic address situates you in the hierarchy of structures we discussed. You're at a specific point in space, in a specific galaxy, in a specific region of the observable universe. But, quote 10, your depends on reference frame. The universe has no absolute centre or special locations. You could equally say the observable universe is centred on you, since that's your observational perspective. From your location, the cosmic horizon is 46.5 billion light-years away in every direction. This defines your observable universe, the region from which light has had time to reach your eyes. Someone else, in a distant galaxy, has their own observable universe, a sphere of the same size centred on their location. Your observable universes overlap but aren't identical. You each see slightly different portions of the cosmos. If the universe is infinite as it might be, then your observable universe is an infinitesimal patch of the whole. Yet it's your patch, the only one you can ever experience directly. Everything you've ever seen, every star in the night sky, every galaxy in photographs, every bit of the cosmic microwave background, all lies within your observable universe. It's your window on the cosmos. This perspective personalizes cosmic scale. The 93 billion light-year observable universe isn't an abstraction. It's the actual spatial extent of everything you could possibly observe, the arena of all your potential experiences of the universe. You're also situated in time. You exist 13.8 billion years after the Big Bang, in an era when the universe is middle-aged. Stars are still forming, galaxies still evolving, but the universe's most active period is past. You live in a privileged epoch for cosmology. The cosmic microwave background is still observable. Distant galaxies haven't yet receded beyond the event horizon. You can study cosmic history through observations. This temporal positioning is as specific as your spatial location. You're here now, in this place and time, with this particular view of the universe. Your existence is also improbable from a cosmic perspective. You're a complex configuration of atoms, organized into cells, tissues, organs, a functioning conscious being. The specific arrangement that is you is unlikely, arising from countless contingent events in cosmic and biological history. Yet here you are, real and conscious, contemplating the very universe that created you. Your atoms were forged in stars, scattered through space, gathered into Earth, organized by life into your body. You're made of the universe. You're not separate from it, but part of it. Every atom in your body was once in the primordial fireball of the Big Bang, later in stars, eventually in you. This connection is both physical and philosophical. Physically, you're continuous with the cosmos. Philosophically, you're the universe experiencing itself, matter that has become aware. The universe's size provides context for your existence. You're tiny compared to cosmic scales, existing for a brief moment in cosmic time. This can feel diminishing or liberating depending on perspective. Diminishing because it shows how small and temporary you are. Liberating because it shows you're part of something vast and ancient, connected to all that exists. You can choose how to feel about this. The universe doesn't dictate your response. It simply is, large and old and magnificent. You interpret what that means. Some people find cosmic scale frightening, the vastness overwhelming. Others find it comforting, their concerns put in perspective. Still others find it neutral, interesting, but not emotionally significant. All responses are valid. There's no right way to feel about being a tiny, brief awareness in an enormous, ancient universe. It's personal, part of each person's individual relationship with reality. What we can say is that you're here, conscious in this moment, able to think about the universe's size. That's remarkable regardless of how you feel about it. You're experiencing the universe from your unique vantage point. No one else has exactly your perspective, your location in space and time, your particular consciousness and experiences. In this sense, you're special, not because the universe revolves around you, but because your viewpoint is unique and unrepeatable. When you observe the night sky, you're seeing something no one else sees in quite the same way. As you rest tonight, you can hold this awareness gently. You're part of the universe, a small part, but part nonetheless. The vastness that contains you is real, measured, understood to reasonable precision. You exist within the observable universe, that 93 billion light-year sphere. Beyond it are regions you'll never see, possibly infinite space extending forever. But here, in your observable patch, you live and experience reality. This is your cosmic home, vast yet finite in what you can observe, ancient yet still evolving, understood yet still mysterious. You belong here, brief as your existence is, small as you are in cosmic scale. Rest in that belonging. Let the universe's size surround you conceptually, holding you in space and time, connecting you to all that exists. Your home in the cosmos, here now, real and aware. Let's think quietly about numbers and infinity, the mathematical concepts that help us understand cosmic size. There's something peaceful in contemplating pure mathematics, the abstract patterns underlying reality. 93 billion light years. This is a specific number, definite and finite. We can write it precisely, about 9.3 times 10 to the 25th meters. It's large, but not infinite. Compare this to infinity. Infinity isn't a number, but a concept, representing endlessness. You can't count to infinity, can't reach it by adding finite amounts. It's qualitatively different from any finite number, no matter how large. If the universe is infinite, its size is literally beyond number. No finite measurement could capture it. The 93 billion light-year observable universe would be an infinitesimal patch, 0% of the whole. This difference, finite versus infinite, is fundamental. It's not about being very large, but about having no limit at all. Infinity is the absence of boundary, not an extremely distant boundary. Mathematics handles infinity rigorously. Set theory, developed in the late 19th and early 20th centuries, provides precise ways to reason about infinite sets. Different sizes of infinity exist, each with specific mathematical properties. The infinity of integers, 1, 2, 3 and so on, is called countable infinity. You can list integers systematically, even though the list never ends. This is the smallest infinity. The infinity of real numbers, all decimal expansions, is uncountable, a larger infinity. You can't list real numbers systematically. There are more real numbers than integers, even though both sets are infinite. These mathematical infinities might apply to the universe. If space is infinite, there are infinitely many points. If the universe contains infinite matter distributed uniformly, there are infinitely many particles. The mathematics gets abstract, but it's relevant. If cosmological calculations involve actual infinities, we need rigorous ways to handle them mathematically. Physicists use techniques from mathematics to deal with infinities when they arise. But infinity is also mysterious. Can physical reality be infinite? Does actual infinity exist, or only potential infinity, the idea that something could always be extended further? Aristotle distinguished these two concepts. Potential infinity is a process without end, like counting. Actual infinity is a completed infinite totality. He accepted potential but denied actual infinity could exist. Modern mathematics accepts actual infinity. Infinite sets are treated as completed totalities with definite properties. But whether physical space or matter can be actually infinite remains philosophically debated. Some argue physical infinity is impossible. Physics describes finite systems, and extrapolating to actual infinity might be illegitimate. Others see no problem, arguing that if mathematics allows infinity, physics can too. The universe might resolve this by being finite. But current observations are consistent with infinity. The choice between finite and infinite might be nature's, not ours to decide based on philosophical preference. There's also the question of how many things exist. If the universe is finite, the number of particles, atoms, stars and galaxies is large but finite. If infinite, these numbers are literally infinite. An infinite universe would contain infinite instances of everything. Infinite stars, infinite planets, infinite instances of any configuration you can describe. This infinity of instances follows from infinity of space plus finite possibilities for local configurations. This connects to the multiverse idea. In a sense, an infinite universe is already a multiverse, containing infinite distinct regions, each causally disconnected from distant regions. These thoughts about numbers and infinity might seem abstract, but they're deeply connected to the universe's actual size. Whether the cosmos is finite or infinite is a question about whether physical reality instantiates mathematical infinity. As you rest with these ideas, there's no need to resolve them. The universe's finiteness or infinity is unknown, perhaps unknowable. We can contemplate both possibilities without deciding. There's beauty in the mathematics regardless. Finite numbers, counting the observable universe's extent. Infinite sets, describing what an endless cosmos might contain. Both are elegant, each in their own way. The cosmos might be 93 billion light-years across and no more, a vast but finite arena. Or it might be infinite, extending forever without bound. Both possibilities inspire wonder. Let the numbers and concepts flow through your mind gently. 93 billion light-years, a definite distance measured precisely. Infinity, a concept beyond measurement, representing endlessness. You exist in space with one of these properties. Either you're in a finite cosmos, or you're in an infinite one. You'll probably never know for certain which. But both possibilities are magnificent, each in their own way. Rest in the mathematics, the clean precision of numbers, the profound mystery of infinity. These aren't just abstractions, but descriptions of reality's extent, the universe's actual size. Mathematics and physics meet here, abstract concepts and concrete measurements coming together to describe the cosmos. It's beautiful, this interplay of thought and observation, number and nature. Sleep can come gently, with numbers and infinity floating peacefully through awareness, not demanding understanding, but simply being present, part of the conceptual landscape of cosmic scale. There's something profound about living in an era when the universe's size has been measured. For most of human history, this knowledge didn't exist. Let's appreciate the privilege of knowing what we know. A few centuries ago, the universe was thought to be much smaller. The stars were on a celestial sphere just beyond Saturn, all at the same distance. The cosmos was cosy, human-scaled, comprehensible. When telescopes revealed more stars and more beyond those, the universe grew in human understanding. But the scale remained unclear. Were stars scattered through infinite space, or did they cluster in a finite island? The discovery that the Milky Way is a galaxy among many in the 1920s expanded the cosmos dramatically. Suddenly the universe contained billions of galaxies, each with billions of stars distributed across millions of light years. The discovery of cosmic expansion, also in the 20s, added temporal depth. The universe had a beginning, a finite age, implying a finite distance light could have travelled. The universe became vast but bounded. Over the following decades, measurements accumulated. The expansion rate, the universe's age, the density of matter, the properties of dark energy, all were determined with increasing precision. Now, we know the observable universe's size to within a few percent. 93 billion light-years across, containing 2 trillion galaxies, 13.8 billion years old. These aren't guesses, but measurements, as reliable as any in science. We also know the universe extends beyond what we observe. The flatness and uniformity tell us it's much larger, possibly infinite. This isn't direct observation, but reliable inference from well-tested theories. Imagine explaining this to someone from the past, a medieval scholar, a Renaissance philosopher, an Enlightenment scientist. How could they grasp the scale we now understand? They'd be amazed at the numbers, the techniques, the instruments we use, the cosmic microwave background, satellite observations, general relativity. None of these existed in their time. We stand on their shoulders, building on centuries of accumulated knowledge. But we've also gone beyond anything they imagined, measuring the cosmos itself, determining its size and age and structure. This knowledge is a gift of our epoch. We live when observations are rich enough to constrain cosmic properties, when theory is sophisticated enough to interpret observations, when technology is advanced enough to measure precisely. Earlier generations couldn't have known. The universe was too young for many cosmological observations to be meaningful. The cosmic microwave background existed but wasn't detectable without modern instruments. Later generations might not know as easily. If we're right about accelerating expansion, future observers will see fewer galaxies, making cosmology harder. They'll need preserved knowledge from earlier eras, like ours, when observations were rich. We're in a sweet spot, cosmologically speaking. The universe is old enough that we can observe deep history, but young enough that much remains visible. This privilege won't last forever. Appreciating this privilege means recognizing how fortunate we are to live now, when such knowledge is accessible. Not everyone throughout history could know what we know. It also means recognizing the human achievement involved. The measurement of cosmic size represents thousands of scientists over generations, each contributing observations, theories, instruments, analysis. It's a collective accomplishment, built through international collaboration, shared data, peer review, gradual consensus. No single person measured the universe, but humanity collectively did. This knowledge is now part of human heritage. Future generations will inherit it, building on it, perhaps refining it. It's a lasting contribution, like great works of art or literature, but expressed through science. There's also intimacy in this knowledge. We've measured our cosmic home, determined its size, understood its structure. It's like finally mapping a place you've lived all your life, seeing the full extent of familiar territory. The universe is where we exist. Knowing its size grounds us, provides context, helps us understand our place. This isn't abstract knowledge, but deeply personal, even if cosmic scale seems impersonal. We belong to a universe 93 billion light-years across, possibly much larger. We've measured this, we know it, we can contemplate it. This knowledge connects us to the cosmos in ways previous generations couldn't access. As you rest, you can hold this privilege gently. You live when cosmic scale is known. You have access to measurements, images, data that reveal the universe's extent. You don't need to have made the measurements yourself. The knowledge exists, publicly available, part of human understanding. You can read about it, think about it, appreciate it. This is the privilege of living now, in this era of cosmic discovery. The universe has been measured, its size determined, its properties catalogued. You're alive to know this, to wonder about it, to feel whatever you feel about inhabiting such a vast cosmos. Rest in that privilege, in the knowledge that exists, in the human achievement it represents. The universe's size is known, at least the observable portion, and you, living now, can know it too. In these quietest moments, let's simply rest in the immensity, not analysing or understanding, but just being with the vastness that surrounds us. 93 billion light-years. Let the number exist without needing to comprehend it. It's there, definite and real, describing actual space. Beyond our horizon, more space. How much more? Unknown, possibly infinite. The thought can simply float, unanswered, peaceful in its mystery. You're somewhere in this vastness, a specific location, Earth in the Milky Way, in the local group, coordinates in space defining where you are. But where loses meaning at cosmic scales. Everywhere is equivalent. Your location isn't special, but it's yours, your vantage point on the immense whole. The cosmos extends in all directions, above, below, if such terms mean anything in space, north, south, east, west. Every direction leads to more space, more galaxies, continuing to the horizon and perhaps beyond. This extension is peaceful. The universe simply is, vast and patient, existing without purpose or intention. Just space, matter, energy, following physical law. No urgency in cosmic expansion. It proceeds at its own pace, unhurried, inevitable. Galaxies receding, space stretching, the universe growing larger. You don't need to track this expansion. It continues whether you think about it or not. The universe does its thing, vast and impersonal and ongoing. Yet you're part of it, made of its matter, existing in its space, subject to its laws. Not separate but continuous, one small arrangement of atoms in the cosmic whole. This belonging is peaceful. You don't have to maintain the universe or understand it fully. You simply are within it, held by space and time, part of the pattern. The vastness that intimidates can also comfort. Your concerns are real but temporary, local but not cosmic. The universe continues regardless, providing perspective. Problems that loom large shrink against cosmic scale. Not that they don't matter, but they're contained, part of your small corner of vast space. The universe's size makes room for everything. All human joy and suffering, all history and experience, all life throughout the cosmos if it exists, everything fits in the immensity. Nothing is too large for the universe to contain. It's spacious beyond comprehension, accommodating all that exists with room to spare, possibly infinite room. This spaciousness is restful. There's no crowding, no limitation. The universe provides abundant space for all configurations of matter, all possibilities, all variations. You could travel forever in an infinite universe and never exhaust the space. New regions always ahead, new galaxies always beyond, continuing without end. Or you could remain still, right here, and the universe continues around you. Space extending outward, galaxies orbiting, expansion proceeding, all while you rest. Both are fine. Motion or stillness, exploration or contemplation, the universe accommodates all. It's indifferent but not hostile, neutral but not cold, just vast, peaceful in its vastness, quiet despite containing billions of galaxies, still despite constant motion. These paradoxes exist comfortably in cosmic reality. As sleep approaches, the immensity can be a comfort. You're held by something larger than yourself, contained in space that extends beyond imagination. The universe cradles you, not intentionally but naturally, as space cradles all matter. You exist within it, supported by physical law, connected to the cosmic whole. Let the size wash over you. 93 billion light years, possibly infinite, definitely immense. The numbers fade, leaving just the sense of vastness. This vastness is your context, your environment, your home. Peaceful immensity surrounding you, extending forever or nearly so, real and present even as you rest. Sleep can come in this immensity cradled by space, part of the vast cosmos, tiny but belonging, brief but real, held by the universe in its peaceful expanse. In these final moments together, let's rest in the simple fact that the cosmos has been measured, its size determined, its properties understood, at least the observable portion. Scientists have measured the universe. This isn't metaphor. They've calculated distances, plotted cosmic expansion, determined the observable universe's radius with precision, 46.5 billion light-years in every direction. This defines your observable sphere, the region from which light has had time to reach you. This measurement is real, based on observations of ancient light from the Big Bang's afterglow, based on general relativity's equations describing cosmic expansion, based on careful work by many people over many years. The number might be refined slightly as measurements improve, but it won't change dramatically. The observable universe is about 93 billion light-years across. This is established fact. Beyond observation, there's inference. The universe is flat, or very nearly so. This means it's much larger than observable, possibly infinite. We can't measure the total size if it's infinite, but we've determined it's at least hundreds of times larger than observable. That's meaningful knowledge, constraining what's possible. These aren't speculations, but conclusions from rigorous science. The universe's properties determine its geometry. The geometry determines whether it's finite or infinite, and if finite, constrains its minimum size. All this knowledge exists. Measurements made, calculations done, conclusions reached. The cosmos has been characterized, at least the accessible portions. This is human achievement on a grand scale. We've measured the container of all existence, determined its size and age and structure. Not perfectly. Uncertainties remain. Questions persist. But the broad outline is clear. The universe is large, old, flat, expanding, containing vast amounts of matter and energy. You can rest in this knowledge. It exists whether you understand all details or not. The universe has been measured. The work is done. The knowledge is recorded. This is your cosmic context. You live in a universe 93 billion light-years across that we can observe, possibly much larger beyond our horizon. This fact holds true regardless of what you're experiencing personally. Your mood doesn't affect cosmic size. Your problems don't change the universe's geometry. There's peace in this. The cosmos is what it is, measured and characterized, existing independently of human concerns. You're part of it. The same matter, the same physical laws. But you don't bear responsibility for it. The universe manages itself through natural law. As you drift towards sleep, you can let cosmic scale surround you conceptually. measured space extending 93 billion light-years. Possibly infinite space beyond, all of it real, all of it existing now, simultaneously with your present moment. Galaxies scattered throughout, following their orbits, indifferent to human observation. The measurement doesn't change the universe, it changes human knowledge. Now we know what we didn't know before. The cosmos has revealed its size to patient observation. This revelation is complete for the observable portion. The 93 billion light-year figure won't change significantly. It's as determined as cosmic knowledge gets. Beyond that, mystery persists. Total size unknown, possibly infinite. This mystery is comfortable now, not threatening. We've measured what we can. What remains unknown is simply beyond current reach. That's acceptable. Science doesn't require complete knowledge. Understanding the observable universe is tremendous achievement. The rest can remain mysterious. Rest in what's known. Measured space, determined size, characterized geometry. The observable cosmos fully mapped in its broad structure. Rest in what's unknown too. The extent beyond observation, the question of infinity, the mysteries that persist. Both knowledge and mystery are peaceful. The measured cosmos holds you. 93 billion light-years of characterized space, extending beyond to unknown but possibly infinite reaches. You belong here, in the measured portion, in the unknown beyond, in the cosmic whole whatever its total size. Belonging not through earning, but through existing. Being part of the pattern. Sleep comes in this measured cosmos, this characterized space, this universe whose size we finally know, at least the observable portion, at last after centuries of wondering and measuring. Good night. Rest in the measured immensity. The universe is large. We know how large, at least where we can observe. That knowledge surrounds you, contains you, holds you as you rest. Thank you for staying with me through this long, gentle journey through cosmic measurements and the universe's vast size. We've spent 2.5 hours together, moving from observable boundaries through measurements and implications to contemplation and rest. I'm grateful you chose to spend this time exploring how large the universe truly is. We've travelled together through many ideas. We explored the observable universe, 93 billion light-years across. We distinguished between different size measurements, understanding particle horizons, event horizons, and total extent. We examined the universe's geometry, finding it's flat or very close to flat. We contemplated infinity and what it might mean if the cosmos extends forever. We thought about the cosmic microwave background, the ancient light that helps us measure cosmic scale. We explored what lies beyond our horizon, regions we can never observe. We studied expansion history, from inflation through matter domination to current acceleration. We looked at cosmic structures, from planets to superclusters, seeing how they nest within the vast universe. We understood the difference between light travel time and actual distance, how expansion complicates cosmic measurement. We contemplated topology, whether the universe wraps around on itself or extends infinitely. We distinguished observable from actual, recognizing our knowledge's limits. We explored why size matters, how it affects our understanding of cosmic origins, evolution, and fate. We thought about multiverse theories, philosophical implications, and what we can never know. We appreciated the history of cosmic measurement, the role of inflation, the limits of observation. We reflected on meaning, privilege, and immensity. And now, as we reach the end, let's return to the simple fact at the heart of our journey. Scientists have measured the universe's size. The observable portion is 93 billion light-years in diameter. The total universe is much larger, possibly infinite. The answer to how big the universe is, as clearly as I can give it, is this. The observable universe is 93 billion light-years across, measured precisely through cosmic microwave background observations and cosmic expansion calculations. The total universe is at least hundreds of times larger and might be infinite. The observable portion is well determined. The total extent remains uncertain, constrained, but not fully known. Probably the universe is either infinite, extending forever without boundary, or finite but vastly larger than observable, with the choice depending on whether its curvature is exactly zero. Current measurements support flatness, suggesting infinity, but can't rule out tiny curvature that would make the universe large but finite. If you enjoyed this slow drift through cosmic measurements and vast scales, a like and subscribe helps others find these calm explorations. And if you have thoughts about the universe's size, about infinity, or about our cosmic home, the comments are a space for sharing. To those already part of this community, thank you for being here, for bringing your curiosity to these explorations of cosmic immensity. Wherever you are in the world right now, I hope you found some peace in this journey. I hope your breathing has slowed, that the day's concerns have faded to background, that your thoughts have expanded into the vastness we've been contemplating. I hope you feel connected to something larger, held by the cosmic immensity. Look up at the stars if you can see them from where you are, or imagine them if you can't. They're scattered through space extending 93 billion light-years to the observable horizon, and possibly much farther, perhaps infinitely far. All that space is real, measured or constrained by science, understood through patient observation and careful reasoning. The cosmos has revealed its size, at least the accessible portions. The mystery of the total extent remains. Finite or infinite? We may never know for certain, but the observable 93 billion light-years is determined, measured, known. Sleep well tonight. Dream of vast spaces extending in all directions, of measurements made across billions of light-years, of horizons at the edge of observation. Dream of flatness implying infinity, or implying enormous but finite extent, both possibilities magnificent. Dream of the universe measured and unmeasured, known and unknown. The 93 billion light-years we observe and the possibly infinite reaches beyond. Dream of humanity's achievement in measuring the cosmos, determining its size after centuries of wondering. Dream peacefully, knowing that the universe is large, larger than we can comprehend but not larger than we can measure, at least the observable portion. Dream knowing you're part of this measured immensity, belonging to space that extends 93 billion light-years and perhaps forever. Good night. Rest in the measured cosmos, in the vastness we've determined, in the larger vastness we've inferred, in the universe whose size we finally know, at least where we can observe. Sleep well, and when you wake, you'll still be here, in this enormous universe, small but part of it, temporary but real, held by the cosmic immensity. Good night.